Let's start. Okay, this is okay. Okay, so in the last class, we were discussing about overfitting, and we found out that there are two types of noise primarily we thought of. One is the stochastic noise or the actual noise in the data points, which means that not all the points are perfectly fitting your target function as well. There is a little bit of noise on that. And what your function or hypothesis is trying to do is trying to exactly fit those points, and that's why it is also fitting the noise inside it, which leads to overfitting. The other part we also have seen is the deterministic noise, meaning that the target function could be more complicated than your allowed hypothesis or the model, which means that inherently in the target function you cannot fit. So it's a deterministic noise, so to be so called, because it is not the actual noise in the data, but it is the incapability of your hypothesis model to fit in the actual target function. And we try to see that there are ways in which we could deal with overfitting, and we have one remedy of such called regularization and one is called validation. So, but also we could think this problem as that when the definition of overfitting says that when the in sample is still reaching towards a lower limit in terms of the expected error, the out of sample beyond a certain point grows up. That means at that point you are trying to overfit more. With the more number of data you get in, you are trying to fit those data to in a too strict manner. We have seen the role of deterministic and stochastic noise as well. We have seen the more the training data, the less the overfitting is, because now you know the structure of your data points more clearly or can visualize your target function more clearly. However, if the noise level grows up, you see more overfitting, as you can see in the left figure. And if the target complexity grows up, that means your target is of higher order polynomial, and there is a chance of overfitting because the number of points doesn't reveal that higher order polynomial always. One point a pertinent point to note along with this fact is that what is the relation of the generalization bound in VC dimension, that we get a bound with respect to the out of sample and in sample. So if we overfit also, that bound doesn't get lost. It allows the bound because the bound is too pessimistic. But your VC dimension generalization bound is so pessimistic that usually your effective E out will be much lesser than that omega tolerance that is given to you. So it never predicts that, but it allows that bound even in overfitting. So there is not a new deal we are making here in overfitting. We are still under the realms of generalization bound, but it's too strict. Generalization is too loose there, and otherwise, in general case, if we do not overfit, it is a little bit better scenario we reach. So as you can see that there are two ways. One is that how do I not fit the noise is mostly when your problem is ill posed. I would say that because you have a noise, that meaning that the problem is ill posed and you want to too heavily try to fit the noise. So you need to approximate your hypothesis much better or make the hypothesis much smoother. So as to say, the smooth is a very English term. We will mathematically define what is smooth, so as to fit it properly, not going to overfit it. And the other thing we can do is that we can handicap the E in reduction. Somewhere down the line, we can stop it somewhere. And there the validation will also come into picture, that when we can stop it, and further we will not go into producing lesser number of E-ins. So this week's coverage is primarily, today's class will talk about regularization, and the tomorrow's class will talk about the validation, the two de facto remedy in machine learning. And remember that without these two remedies, your algorithm will never sustain in practical position. So in practical scenario, you must have to use regularization to stop overfitting, and validation also in order to get rid of this problem. We will see that how regularization applies in today's class. Remember this curve earlier, that we want to fit the sign with respect to only 2 points. And in this, since we are trying to join the 2 points with a line, if the hypothesis was a line, we landed up in such kind of a bias and variance factor. So in case of the first thing, it is trying to fit this thing without regularization, and we found that our bias was good, 0.21, because two points we are trying to fit in a line, the bias is almost getting close to the target function. But we found our variance to be a very horrible one, which kills the performance of the out of sample error. So here also in this problem, regularization comes into rescue. What we try to do, instead of abruptly trying to allow every possible fits, we try to restrict it within a set of fits. That means we will not allow, so we do not allow all slopes in order to fit the points. So which in short has, what it will do is that it will reduce the bias factor, the variance factor to a greater extent. Now, if you do not allow every possible slope, obviously your fit that we are doing here and the fit that you are doing here will not be the same, because that is the average hypothesis considering all the lines. Now, some of the lines are truncated, so you are not allowing those slopes. So therefore, your average hypothesis will also shift. So your bias will also change definitely. But with that, we will get a greater impact on variance. So what we did is that the learnability with respect to those points through a line, we make it a much smoother rather than this abrupt. So that's what I call it a smooth. A little bit making it smoother is also going towards regularization. And indeed, if we try to see that bias little bit grows up, but variance has a drastic impact on it. And now when you go for bias and variance, this not only improves upon without regularization factor, but also beats the only the hypothesis when my hypothesis was fx equal to x, sorry, fx equal to ax plus b. This is also better than when my hypothesis was just a constant. So this also performs better in after regularization. So that is the impact that we will try to make in when we try to say that we will try to not fit noise too much. Here also, when we allow the other slopes, so these slopes are basically noise with respect to the target that you want to achieve, isn't it? Because if you get points like this here and here, if you get points like here and here, and you try to fit in with this line, so this is nowhere near your best fit possible. So these are your noises you are trying to fit in terms of colloquial terms, we can call it. It's a noise we are trying to fit in, and hence we are trying to justify this fit in a heavy manner. So our bias and variance width becomes so large that we get a bad performance earlier, and regularization will do it. So we will try to mathematically now formulate what does regularization mean, and try to see why this kind of a constrained solution give us benefit. So it is nothing but constraining the solution space, which we call the regularization in colloquial terms. So let us try to ask us that, suppose I want to fit a set of data. Let us try to take our general linear regression kind of a problem. I want to fit a set of data using polynomials. So when we say that we will try to fit a data using polynomials, so effectively your data could be second order polynomial, third order polynomial, fourth order polynomial, and so on. So therefore, what you say that my hypothesis class, as I have shown, that I will take only the polynomials of order q. So this is the hypothesis class of all polynomials up to order q. That means this is wq. So if I see this one, I will later say why I will take this kind of a polynomial. So these polynomials are called Legendre polynomials. I could have taken some other polynomials as well, but since I would like to compose between them, these are orthogonal in nature. We could have taken monomials as well, but monomials are true correlated. So when we compose L2 with L3 and get a third order polynomial, if we do not take such kind of a Legendre kind of a polynomial which are orthogonal to each other, then the terms that may also correlate with each other. That kills our purpose of finding new polynomial structure out of only this polynomial. So these are generic polynomials, and it's a mathematical concept of scientist called Legendre, who generated that the compositions of these polynomials will effectively land up into something which are not linearly dependent. So therefore, our hypothesis class that we are trying to make is essentially, we will think of it's a composition of such polynomials of 0 up to order q, wq, and we will take this Legendre polynomial to compose it. So what does it mean is the fact that I have a set of points x1 and its output y1. These are my training points, and xn its output yn. What I will do, I will try to make a transformation with respect to these polynomials. So L0x is 1, L1x up to LQx, so that these points gets transformed into the space of z's, z1 with the level y1 up to zn with the level yn. Now, why I will like to do that? Because such kind of a transformation later we are trying to constrain. So depending on the constraints that I make, I could make some WQ as 0 and some WQ as 1 as well. So if I make a WQ 0, so that ordered polynomial is no longer used. So if I make L5 WQ W5 to be 0, then x to the power 5 polynomial will not be in my case. So I will fit a little bit lower order polynomial. So that's why whenever I get a data, what I will try to do, I will try to apply this Legendre polynomial structure in G space or the Z space we have, and transform those points over the polynomial that we want to find out. Now see, the linear regression over this space is nothing but trying to minimize. If you look at the linear regression construct that we can do, we try to minimize the set of weight vectors, where the minimization is the sum squared error, as we already know for all the points that we have, which is Wt in this Z space Zn minus Yn square. And we have seen that we can also write the same using the capital Z comes in here with W minus Y transpose into ZW minus Y, because these are two matrix, transpose into this will give you the squares for every iterations. We have seen that. And when we try to minimize such thing, we have seen that the linear regression has produced this as our answer. I call it WLin as the linear regression answer, and which is the pseudo inverse that we compute one step linear regression learning. So this is the weight that I finally get that gives me minimum E in the minimum E in W, the error in the in sample. That's how linear regression works. There is nothing new with it. It's the colloquial linear regression. The only thing is that I want to fit the points in such a way that I want to fit it in terms of a polynomial structure. And it's obviously, if you do a linear regression, it's an unconstrained fit. I'm not constraining anything. Unconstrained fitting of endpoints. And finally, when we minimize this WLin, it will give the minimized value of all the WQs for all Qs. And the polynomial that you will get will be a qth order polynomial. If not the final W capital Q is 0, then it will not be the qth order. Till a point it is non-zero, it will be that ordered polynomial that you answer as the final linear regression line as an outcome. So this is unconstrained fit. Still, we do not do any regularization, nothing. So it's just, I want to visualize my linear regression in terms of a polynomial. I will take Legendre polynomial due to certain advantage we have. It's less correlation, and try to find out what combination of this polynomial or which order of this polynomial is best fit, which I will minimize by my one-step learning algorithm, as we have already learned. Okay. Now see, when in the last class we declared that instead of using H10, if you remember, we have declared two hypothesis classes, H10, which is a 10th order polynomial we are trying to fit, and H2, which is a second order polynomial. This is a smooth one, and this may be like this 10th order polynomial. This is also making certain constraints into this. Why? Because H2 is nothing, this H2 is nothing but HQ with WQ equal to 0 for Q greater than 2. Isn't it? This is a 10th order polynomial. If I constrain that 10th order polynomial to have like H2, I have to constrain all weights beyond Q greater than 2 to be 0, so that the polynomial compositions that I get will be a second order. So it's a two hard constraints, I would say. It's a hard constraint that whenever you are overfitting with H10 and you are coming down towards H2, you are making a very hard constraint, which means that you are just neglecting certain orders of a polynomial and jumping from the higher order to the lower order without taking these orders at all into the picture. It's a hard constraint. But maybe that your something would lie in between this, that it may need something this and something this. That's what I mean by smooth. It may not be a hard jump, that your data may not be always a fifth order polynomial or a sixth order or a fourth order. This is a higher jump, but in between these polynomials there are smooth regions which also needs to be needs to be seen in order to see whether I can reach to a better fit solution without overfitting. So though this is a hard constraint, we can also impose a softer version of that constraint. So again, here also we would like to find HQ, which is nothing but sum of finding the weights with respect to these polynomials. Rather, we will give this soft constraint now instead of hard, that I will give you a budget of using total W's. And I will tell you that I will only give you a budget of the sum square to be less than equal to some constant C. Which means that if you use it too much for the higher order polynomials, you will not, this budget will exhaust and you cannot use it for lower orders. If you use too much for the lower order polynomials, this budget will exhaust and you cannot use it for the higher order polynomials. So instead of giving a hard constraint that you stop being taking a polynomial up to this order, or maybe taking a polynomial don't below this order, we give you a soft constraint so that we could navigate through the search space and find out the optimal in between lines of smooth curves. So similarly, our problem now will be the same, that we want to minimize E in W, which is basically nothing but 1 by n ZW minus Y transpose into ZW minus Y, subject to the constraint that this one I can write it as W transpose W, because it's nothing but a sum of the squares. So W transpose W less than equal to C. So this is the problem. If I could solve it properly and I could give a proper choice of C, that I will later say, that this C is just a kind of a regularization parameter, that how much smooth I want to make it or how much allowance I want to give it. Depending on that, the solution I will get, this will be a regularized solution of the weights, and can find out finally what is my final fitting curve or the final fitting polynomial would be. So here I want to land up, and this is the steps of regularization that I want to make. Problem statement clear?
Sir, I have two questions.
Mm-hmm.
Sir, at port number 3, we are assuming that WQ equal to 0 for all Q greater than 2. Then why we
If you
consider this?
if you consider only second order polynomial up to that.
Obviously, I understood that. But within L2 to L3 curve, this polynomial session, why we consider these things? Because L2 to greater than L2 should be discarded from that equation. Na? Q greater
Yeah,
than 2.
but suppose I want something of L1, something of L2, and something of L3. Then how
Wha-
can you do that? Either you have to discard a portion. You can take only a range, like I want L3 and L4 inside it, not others, if with these hard constraints. But what if my curve sometimes, I mean, in between these L1 and L2 and L3, it's a linear composition of these three is your actual answer. Or it's a linear composition of L1, L2, L4, L6. That you cannot do
Okay.
by just eliminating, right?
Hmm.
That's why we need to have a softer constant. I mean, that's why the generic problem of regularization is this one. Here also, you can easily use C with if you want to allow only H2, you use the full C with W1, W0, W1, and W2. Use the full
Hmm.
C with these three, and rest zero
Obviously.
for
Hmm.
everything else. That will do.
Yes. Hmm.
But this will also help you to find out a solution, a better solution, which may consist of L1, L5, L7, L9, L11, L12, like that, arbitrary. So
Q
this is the
greater than
generic
2. For the
which one.
value Q greater than 2.
Q you do
No.
not know. That's the question. Q you do not know. Only you know it's a qth order polynomial which whose highest degree is, let's say, 50.
Oh, acha, acha. Hmm.
So that is a generic constraint, nothing more, much more than that.
Okay, okay. Hmm. Thank you,
However,
sir. I
if you
got it. Hmm.
yeah, if you now see this problem, isn't it resembling something you have already studied? Can you remember? Suppose
Yes, we
vector. Yes, yes,
Yeah, the
yes. We solved.
Lagrange's multiplier.
Yes, yes. We solved such constant using Lagrange multipliers and all. And Lagrange multipliers, as you can understand, these multipliers are these ones. So today, instead, you know how to apply KKT theorem and make it a dual formula and solve for alpha and all. You can easily do it here because you have studied SVM. Today, I will give you another intuitive view of the same solution, which will then easy to understand the both things together. So let us try to intuitively solve it. What we are trying to do here, let's say we are trying to minimize E, which means suppose I have, so E is a contour of such kind of a circle, I mean ellipsoid. So it's a, you can find it as just a cup like shape. So inside it, if you go in, your E in is everywhere. E in here in the boundary points are same. Here is less than this point, here it is less. If you go in somewhere down the line here, your E in is minimum. Okay. So that solution, irrespective of the constant, we called it as W lean because there was no constant. We are only minimizing this one. Now your weight space imposes a constraint like this. It will be of circular nature because it has a square kind of a quadratic term. So therefore, your weight space now has this structure where this circle is WTW equal to C, the equation of the circle. And in between this point is, since you need this less than equal to C, so any point inside it adheres to this constraint. Now see where in will also be less subject to this constant is met. So obviously I would like to be in the boundary of this, isn't it? Boundary of the pink circle where in is also less and this constant is I need to only obey. So my obeying will also happen if I be in the boundary. Agreed?
Yes, sir. Agreed.
Now, if this was much more relaxed, what will happen? If this was much more relaxed, your circle could have been like this, right? I mean, if I draw the circle, your circle could have been like this, incorporating this point. If you seize too much, so it doesn't matter in our analysis because our solution then would be this one, because it is satisfying the constant. My circle is bigger, so anything inside point where the error is minimized will be my solution. So only the interest point would be when I have this kind of a scenario where the circle is lesser than the W lean point. So your W lean will not be your W range because your W range needs to obey this one. So now if you think more theoretically, suppose there is a, so as you can understand, the point would be just like this where, so if I take a point like this, it will be explained in a minute. If I take a point like this, so this is an ellipsoid. So therefore there will be a component here which says delta E in W, which is just in this ellipsoid, if you think a three-dimensional ellipsoid, it is perpendicular to the tangent in that point. Similarly, from the center, the W will be again perpendicular to this tangent. So this will be the normal W's that you can get. So see, there is an angle between it and it is not 180 degree. That means there is a chance of improvement if you move along this line. So when you will freeze at a point like this where both are 180 degree apart. That is your solution. And that solution is your W range that I will get by solving this. Right? As you can see, this solution is nothing but this is going away from this center and it is just so. So if I want to say E in W range, the solution value with W range, it is nothing but it is proportional to minus W range, because this is the W range in opposite direction of this vector side. So it is proportional to minus W range. This will provide you a solution. Now let me add this proportionality in terms of certain constants. Why I am adding the constants? When I derive, it will be easier. Let me add this constants with it. I can add any constants with it. Sorry. Just wait a minute. Okay, so I can add any const. I mean, I can add any constants with it. So why I add this one, it will be immediately clear when I write you the equation. So therefore, you can see this is a solution W range, and as I can see, the solution is in the opposite direction of this vector line. I mean, with respect to this circle, and it gets pulled towards this, but it cannot go beyond it due to this constraint I have in my hand. Now, isn't it giving a very nice equation like E in W range plus 2 lambda n W range is equal to 0? Why it is a nice equation? Because how this thing will come? If I minimize E in W plus lambda by n WTW. Isn't it? Because if I minimize this, a delta will come in here. If you differentiate this one, the 2 will come out here, and this will give you the, if you give a delta, I mean, differentiate this and make it 0, you will exactly get this equation. And the answer will be W range. So I just put W range here. So what does this bring us? Minimizing this. It brings us that these two are equivalent or duals of each other. Are you getting me? So I started off here with a solution, which I saw that the solution of that gradient will be proportional to W range, because the gradient is the slope and it is going opposite. It's in the direction opposite, and towards the center it is the W range itself, which is the solution. Let's say the solution is looks like this. The gradient looks like this. Why I made it? Because this can be found out from this formula, and which means that if this is the case, if this be the equation, then these two must have to be equivalent. Okay, why I made this one? Now you can, if you remember the KKT's theorem and that the primality and duality conversion, you will see what I made in SVM also such kind of a thing. I put down the constraint into my picture of minimization and try to minimize this one. Yes or no?
Yes, sir.
And I told you the boundary points in this will be the solution having lambda greater than 0. The internal points in this will have the solution lambda equal to 0, which is my alpha earlier. Remember?
Yes, sir.
In SVM. So what does it mean? So let us see. Let us try to see this in more details. Whenever your C is very high, whenever your C is very high, that means what? That you have the constraint to relaxed. Your circle is like this. That means the W lean is your solution. right? If C is very high, then your lambda is almost close to 0. When your lambda is close to 0, that means this term vanishes. And you get W in solution only by minimizing this. Because E in was only this one without any constraint. So you minimize E in and get the W in as solution. Agreed? So these two are indeed the duals of each other. Similarly, if you have C very low, close to 0, then your lambda goes very high, like infinity. When lambda goes infinity, then this term dominates. So when this term dominates, that means if your C is very close to 0, this term dominates. That means whatever be the minimum, you have to give the answer. There is no constraint given to allow me to push towards the boundary. This is the only thing that is possible, which means to minimize this one, I only have one option, that my W range should be 0. That is the center. Right? Isn't it?
Yes, sir. Yes, sir.
So that means if I do not allow you any constraint here at all, I mean, just I allow you whatever be your W, you do not choose any W at all. So you have no provision to go inside the minimizing the error at all. So with respect to the initial random weights, or let's say W equal to 0, whatever be the error that makes you here is your answer. Get this point? So these two are duals and primals, which we established in KKT theorems in support vector machines. We can see the same thing here as well. Okay, here only we mention lambda greater than equal to 0, subject to lambda greater than equal to 0 when we introduce Lagrange multipliers alpha is here. However, you see here this is unconditional. As you can understand that this one is unconditional. This one is a conditionality imposed into it. Why? So since we are solving it here, so why we at all bother about this previous conditional thing? The only point is that here you can apply VC dimension because there is a constraint which prevents you to land into infinite hypothesis space. Here it is out of constraint. So from these equations, you will land up the values of W in infinite sense, whereas this constraint here makes your VC dimensions not unbounded. So it is easier to analyze your VC dimension using this formulation, but easier to solve the problem using this formulation. That's why people try to have a conversation between this and this. Okay. So
Yes, sir.
with that, let us just try to write out what we want to do now with the dual. So we want to minimize, let us say our error has little bit changed. We call it an augmented error because it is augmented not only with respect to E in W, but we also have a term lambda by N W T W. This whole thing we are trying to minimize. If you try to write it more formally, this E in W was my ZW minus Y transpose into ZW minus Y into 1 by N. This 1 by N, if I take out, this is nothing but lambda W to the power T W. This was quadratic in nature. This is also quadratic. So this can be solved by quadratic programming techniques as we do. And when we try to minimize this one, then instead in the earlier case where it were only in the linear regression where there were only the first term, not this one, we get a straightforward pseudo inverse. But here if you do it, you will get this kind of a term. Earlier you get up to this. Now differentiating here also will come with respect to W. So you will get this equal to 0. Now when you get this equal to 0, that means your W reg, that is the solution, is equal to, you club this W with this one, which means it is ZTZ plus lambda into identity. Make it inverse because we have to mix into the Y side. This opposed to our W lin solution, which has only the term Z transpose Z inverse into Z transpose Y. This is not really pseudo inverse anymore because we had a lambda, which is our regularization parameter coming in. But see why this solution is also valid, because now you try to think what happens if your lambda is infinite or it is too huge. If your lambda is too huge, pictorially, what does it mean? It means C is very less. That means I am constraining the solution as if it were just zero weight I am allowing. I am not allowing anything. If your lambda is used, this is to the power minus 1. So it comes in the denominator. So your W reg becomes 0. If your lambda is too small, that means your C is very large. It also encapsulates the W lean inside it, the minimum E in. So if your lambda is 0, you can see this is nothing but the W lean solution itself. Just drop out this term because your lambda is 0. So if your lambda is too small, almost close to 0, then your W reg is almost equal to W lean. You get the impact?
Yes, sir.
So therefore, this is your regularization and this is your without regularization solution. Now let us try to think, what does this regularization parameter brings in? As you can see from here, the regularization parameter is actually dependent on the choice of C, because the C has governed this W. There is a relation, as I have told. So the more you allow this lambda to be, the more value you put in lambda, your circle will be less and less, which means the more value you put in lambda, you have less choice of getting towards the actual linear original solution. So you will always try to find a boundary which is mostly close to this. So making more and more this one will reduce your weight space in such a way that many of the Legendre polynomials will be weighted by 0, because the more you give to lambda, the less you give to C, and you have a budget, which means it will be more flatter in terms of the. So your 10th order polynomial looks like this. The 5th order polynomial will be a little bit flatter. The 2nd order polynomial is totally flatter. Understand? So impact wise, what will happen is that the more lambda you put in, the flatter curves you will try to get. Or we will say that the smoother curves you will try to get, because 10th order curve and the 3rd order curve with respect to all compositions of Legendre polynomials will be little bit more smoother. And what will result, you see the same experiment when we try to fit in. The last day I just gave you this solution. If you give lambda equal to this much, very little, just a little amount of lambda, your solution becomes this. Remember, this is also a 5th order polynomial. No issue of that. But 5th order polynomial with respect to what? With respect to the combination of non-correlated Legendre polynomials, which make it fit like this. If you put lambda more, it will be more smoother. Lambda more smoother. Finally, if you put lambda equal to infinity, it is just like a simple straight line axis parallel. So where we reached is that here we are doing overfitting. We try to make a regularized solution 1. We try to improve the regularized solution 1 to regularized 1 dash, and so on. Finally, we get a scenario which is called as underfitting, because this no longer approximates your target function anymore. This no longer approximates your target function anymore, because it has a very weird behavior with respect to the actual target. So we keep on doing this without knowing that we are underfitting it. So therefore, the choice of lambda is very important. And as you can see, this is the topic that we will cover in the next lecture, because lambda, there is no thumb rule about choice of lambda. It is just you have to choose it, validate it as you've done the projects and know the meaning of validation now. You keep away some points, validate it, and find out which is the best regularizer. Okay, so this is what we do, and you can also always estimate the bias and variance between this overfitting and underfitting issues and all that. Okay, this is the first, I mean the first notion of regularization and how we apply it in terms of linear regression. Now see that instead there is a concept called weight decay in regularization. So what does it mean is that, so instead of one step solution, so here we did a one step solution, right? This one also, and this one, as we know, it's a one step solution of solving this matrix. If I just give you a stochastic gradient descent with stepwise, you are making the descent of the gradients a little bit example wise, or maybe a small batch wise. So remember the gradient descent. So in the gradient descent, what we do, the same thing, we just try to update the algorithm with respect to whatever is in the tth time, minus, as you know, there is a learning rate, and we have delta E in Wt plus 2 lambda by n Wt. This one comes from the equation that we are trying to solve here. So every time I take a point, I calculate this gradient and I descend. However, here is not only the E in is involved, but we also have a drastic term here, the regular due to the regularization factor, this came. So effectively, what you do is this one. If you solve the equation, it is this one minus eta del E in Wt. So if you now think of the stochastic gradient descent, your gradient descent is perfect. However, each time you have a decay in the weight, isn't it? It depends on the lambda. A little lambda like this, a little lambda like this have a decay in the weight. What does it physically signify? Suppose you are in the weight space and you have to reach somewhere. I mean, the weight space says you reach by resultant like this to your some target weight. Now, stochastic gradient descent just only takes you with respect to the error curve slope. You just go on with the error curve. This shrinks the weight a little bit. Instead of going this way, it shrinks a little bit, try to move this way. Shrinks a little bit, try to move this way. What does it mean? Its shrinking is actually due to the constraints that is being proposed in the problem formulation, which means that it do not give you free fit choices. It does not give you free fitting choices so that you could too much go towards fitting the noisy data as well. It always keeps you within a shrinking bound, and it keeps on decaying your weight so that the target going towards the target also changes in a way that you do not hover around randomly like this curve. You do not hover around randomly like this curve and try to fit everything properly, because my weight decay is now trying to keep me stabilized. And as you can see, this I mean, point wise in linear regression, it is very straightforward and simple to go by this. But as you can understand, in neural networks, if you apply, as you know, the neural networks, there are multiple layers participating, and then you are moving towards one layer to another. So if you have to compute in neural networks, this is with respect to the number of layers, number of inputs, number of outputs, all the ith input to jth output in layer L square, where your L will be 1 to L. This is your input will be 0, that is the mandatory one input with respect to the number of nodes that they are in that input in the L minus 1th layer. Your J will be 1 to the number of nodes that you have in the Lth layer. So the computing this one in neural networks will be like this. Apart from the straightforward, we compute it in terms of a square. So this time kind of thing we cannot apply. We need to apply stochastic gradient descent as we do in neural networks and try to figure out the weight decay factor and gradually move towards fitting it in a regularized manner. Okay, these are just the variations I am trying to make. But if you understand the basic concept, it is absolutely that way. Another variation people usually make is instead of only constraining the weights, they also constrain it using this way. Suppose I write the weights by like this. And this is basically, so instead of only containing weights to C, I just have this composition, a gamma Q. What does it impact? So suppose my gamma Q, so one in the impact is that suppose my gamma Q is very much exponentially related to the qth, the highest ordered polynomial that I want to wish. Which means since you have a restricted budget, so it will try to make low order polynomials fit more. Are you getting it? Your budget is same. I have a particular weightage and its importance. If I give too much importance to the higher weight and the total importance is fixed, that means I will try to regularize with lower order polynomial. Yes or no? Agreed this one. Why I get a lower order polynomial if I have a constant like this?
Yes, sir.
Because I have the importance being the same. I give more importance to the higher order polynomial. So if I take one higher order polynomial, let's say 50, to do the over 50 eats up this space. So in order to make a smoother curve, I will try to fit the lower order. Whereas if I have this one, it means that your regularizer is trying to fit high order polynomials, right? So the thing is that why we try to say that our high order polynomials is bad or low order polynomials is good and all, and why we go for the weight decay is primarily because if so, how does the performance of the regularizer will look like? Let us try to plot that first. Suppose this was your expected error. So this is the expected error side. And this is with respect to regularization parameter lambda, as we have seen in the previous slide, that if lambda increases, we cannot fit well. From underfitting, from overfitting, we go to underfitting. Now, if I try to see that earlier without any regularization being made, my error was this. With a little bit of regularization being made, I am reducing to bit, and then suddenly when I underfit again, my error grows up. Whichever data sets with regularization has this property, that means there is a chance in this data set to minimize the expected error using regularization. Now you can say that constraining weights to be large, so this is a constraint I made. It means constraining weights to be smaller, right? The constraints that we made was summation wq square less than equal to c. It constrains weights smaller. You may also argue that what if I constrain weights to be greater than something? It is also a constraint, isn't it? This is a constraint. As this is a constraint, I could have an opposite constraint as well. I could just constrain it to the higher weight, that is the weight growth instead of weight decay. In that case, what we will figure out is that your curve here will look like this. So this is weight growth or this kind of a constraint, and this is your weight decay or whatever be the constraint that we put while solving. Why this is the case? Why the higher orders or being more tuned towards the higher order is not giving us regularization benefits? The primary thing, it's a practical rule, not a theoretical proof, is there. The stochastic noise, whatever we call about the stochastic noise and try to fit it, usually we find it to be high frequency. High frequency in a sense that suppose this is your target fit, your stochastic noise could be arbitrarily ranging anywhere. So it's a high frequency. And when I talk about deterministic noise, when we talk about deterministic noise, we say it is a non-smooth. Why? Because as you can understand that in a deterministic noise setup, when we try to fit in something like this and we are restricted to fit in like this, so what we can fit in is smoother, and deterministic noise is due to the non-smooth nature of the curve. We are resulting to this kind of noise. Now, when we take this type of constant, why the regularization doesn't get much impact? Because higher ordered polynomials is usually non-smooth in nature. Lower order combination of Legendre polynomials is smoother in nature, and that's why I call it as a practical rule. You may be fooled in some data sets, it may not apply, but mostly people go for smoother hypothesis. Because smoother means that is less ordered polynomial which cancels this part. Also, if it is smoother, high frequency obviously is non-smooth, as we have seen here, the points, noisy points. So people go by smoother or sometimes called simpler hypothesis, and it is also a basis of something called Occam razor. It says that you fit with certain hypothesis which is simpler enough, but not the simplest among the lot, which is much more simpler enough. That's why H2 may be sometimes better than H10, depending on the distribution of the data. So that is a practical or the rule of thumb that people try to follow. The second aspect of this regularization, what we see, and after this telling this 1-2 aspects, I will close today's thing. The second aspect that we see is that now your error that you figure out in terms of augmented error, your augmented error with respect to an hypothesis that you get is your whatever be your in plus the regularization constant brings you certain things. Whereas in our VC bound, we have found that E out is less than equal to E in minus there is a constant with respect to the full hypothesis set. Here you see this is with respect to the chosen W range, or that is the chosen hypothesis, you get this kind of an augmented error. However, as we can say that E aug H is more closer estimation than E out H, because E out H is, you do not know that. You do not have test points in your hand. You only have the in sample point. So therefore, E out H is much further estimations than E aug H. So E aug H is always better than, I mean, it's better than E in as a proxy rather than for E out. So this difference, and that's why I said overfitting makes a pessimistic assumption of this generalization bound, due to the fact that I do not see this one. I get an expected value and then Hobding inequality and all that lands me here. However, this is what you can visualize with it, with the constants and tuning the constants, though we will see in validation how we get the lambda value for tuning. But with respect to validations and all, I have this in my hand. So E out, so E augment is better or closer than E in as a proxy for E out. So the whole learning exercise is to minimize this one and tracking that it also minimize E out H. Now we are minimizing this one and tracking this one. So instead of minimizing this one is much more closer, because now I have this one is more than what I need to be minimized through E in. So therefore, this less than equal to gap gets much shrinked with this E augmented. So E augmented H will make you closer estimations, or it is better than E in. So sometimes we say it is better than the estimations that we theoretically get in E in as a proxy for E out. So now in neural network, let us try to see how it behaves in neural network, because in neural network, as you know, that we have a hard threshold and we smoothened it using this tan hyperbolic or logistic function. We smoothened it. What does it look like? See, beyond this point, it is strictly +1. Or maybe you can say that if you take a little bit of tolerance beyond this point, it is +1. Similarly, a little bit of tolerance beyond this point, it is -1. This region is somewhat linear, you can say. It's almost linear. Now, if you have, I mean, if your function has, in weight decay, what we do is that in weight decay, we try to reduce the weights and make the curve smoother so that our weights would make you this sort of range to fall in. Why does it help? Because it comes from the linear boundary. This weight decay makes you towards the logical boundary. So if you grow the weight, you will be in this side, it will contribute higher. If you have a small amount of weight, it will be inside this boundary. As you can see that the function is wixi. So as your weight grows up, you will be in this side, or if it grows very less, it will be in this side. Otherwise, inside it, it is smoother. So depending on that, if you have this small weights, what will happen is a linear combination. So a node, a logistic unit gives you certain linear combination, followed by another logistic unit that you give the linear of linear, followed by another logistic unit that you give linear of linear of linear. So the curvature doesn't change. Only the non-linearity is introduced due to these boundary factors that comes in after you reach to a definitive point when you say +1 or -1. But if you are still in the linear region, so all of them is a linear of linear of linear, it is just a restriction over the linear. So effectively your VC dimension doesn't hamper much. That's why we try to keep these regularizing parameters so that it becomes in the linear region. So finally, when we do in the VC analysis, we have a smaller dimension in that case. And sometimes in VC analysis, then we compute this particular function instead of IJL weight decay directly. We introduce a smoothening parameter beta square and consider this as our weight, the decay of the weight parameter, and we call it as a soft weight elimination. The weight elimination in neural network, instead of only this as a WWT, we have a soft weight elimination, which basically takes a beta parameter, and depending on the beta parameter, you give contributions to the weight to be in the linear region most. So now if you look for the fact that so in this lecture what we did is that then in this lecture the regularization thing we did is dependent on the lambda factor, and the regularization thing is also the regularization fact that we give is also dependent on the basis of the z space that we transform through the Legendre polynomial. Now in validation we will try to incorporate this, how to determine lambda. And the other thing in validation we will try to see is that when we can stop early, as we said that when in goes down, and if we could validate whatever be the data in our hand and could validate at a point where in is no longer going down, we may immediately stop this n and report the hypothesis for this. So for that, what we need to do is we need the full training set D that is given to us. We need to split it using a set for training, and also we need to split it using a set for validation or testing. We will see that the formal notion of these validations in the next class. And finally, before we finish, the optimal value of lambda as per the experiment, we can see that if we have a stochastic noise, as you can see, if there is no noise, your algorithm will absolutely do good. You do not have to give any regularization because there is no noise. Since there is no noise, so the best point is here, your lambda is 0. If you introduce a subtle noise, you can see the curvature here, and you can see that somewhere down the line here, maybe this point is a better approximation of your lambda value to take for regularization. And when your lambda grows up, you can see that we have a better flexibility on the lambda parameter. Similarly, the deterministic noise, this is the QF and this is the sigma square, that is the noise of the regular noise or the stochastic noise. Similarly, the deterministic noise factor, when we see the similar nature. So that's why I told that these two noises are not different in terms of regularization, because we need to give the same thing. So when the QF is lesser, that means actually the target function does not have any deterministic noise than the polynomial ordered polynomial is given to you. You can fit it directly. However, you need a regularization if your target function is of higher complexity. That means you are limited to fit there. So by this, so all this comes from the validation aspect. So you can have an optimal choice of lambda depending on your deterministic behavior of noise and your stochastic behavior of noise. And all these things will be in the part of validation. When can we choose that what is the value of lambda that we are looking for? So with that, I think we are over time also. Let me stop here. And if you have any quick questions, we can answer.
Sir, what will be the value of beta of the last previous slide? Beta
That's what
parameter?
it depends upon where you want to keep it, where you want to keep your weights. See, if beta
It depends on the weights.
Not depends on the weight. The thing is, see, this is what is this? This is your generalization boundary with respect to the weights.
Weight.
Right? Yeah. Now, if your beta is huge, that means you do not want to make you want to bound the generalization error to a very small.
Then beta should be huge.
Then beta should be huge. And if your beta is 0, then you are underestimating with the generalization thing.
Obviously.
So the role of if you look at this curve, the role of regularization is also to generalize, as you can understand. Here the generalization is poor. Here the generalization is it's have a good generalization.
Good generalization.
Right? This again goes poor. So the role of finding a good regularization lambda is also to generalize. Now, this generalization will depend on the kind of parameters that you, or the kind of restrictions that you put in. This kind of a restrictions that you put in. Right? Now, these restrictions will also dictate your generalization. If you put it too much restrictions, you can never get the minimization. If you relax it too much, you will always get this minimization.
Then get the
that will always try to perfectly fit along with the noise. If you relax the C too much. So therefore, you need to wisely choose these parameters so that you get the regularization impact. And as you asked correctly, that what is the value of beta, we get it from validation. We do not drastically take and squeeze it, as we have seen in case of here. That what will be the value of a lambda is better. We need to perform over out of sample. We do not have out of sample. So what we will do, we will create a out of sample, as we have done in cross validation and all, from the training set, and try to estimate this beta lambda value, which is our next lecture, which is validation.
Okay, sir. Okay, sir. Thank you, sir.
But effectively, when you validate and see, you will see this kind of a nature, that noise also dictates the lambda, and also your fitting complexity of the target function dictates the lambda, but accordingly you need to choose.
Yes, sir.
Okay, any other question? Okay, so then I am stopping the recording.